Welcome to this lesson on the beginner's guide to performing polynomial regression in Python using Scikit-Learn. In this lesson, we're going to cover what polynomial regression is, compare the linear regression from last time to see if it's the right fit for your data, and then compare the polynomial and multiple regression models using Scikit-Learn. We're going to compare these models by evaluating their performance using the R-squared and mean-squared scores. Polynomial regression predicts the dependent variable for multiple independent variables when a nonlinear relationship exists between them. Instead of a straight line, the graph for the polynomial regression is a curve. Polynomial regression equation looks like the following. Y is equal to some constant beta sub 0 plus beta sub 1 times x plus beta sub 2 times x squared and so forth. So now we have degrees that are higher than 1 when we're looking at a polynomial regression equation. Polynomial regression captures nonlinear relationships between the independent variables and the dependent variable, y, by introducing polynomial terms such as x squared, x cubed, and so forth. It's still considered a form of linear regression because the linearity refers to how the model coefficients are used in the regression equation. The regression coefficients beta 1, beta 2, and so forth are still applied in a linear manner to the polynomial terms of the independent variable using simple arithmetic operations such as addition and multiplication to combine the coefficients and features in the regression equation. We can evaluate the suitability of a linear regression model to determine if we want to attempt polynomial regression by using a residual versus predicted values plot. The zero horizontal line on the plot represents the ideal scenario where there is no difference between the residuals and the actual predicted values. So the predicted values and the actual values are pretty much the same. And so that's the ideal situation. The zero line serves as a reference point to assess the magnitude and the direction of the deviations or the differences between the observed and the predicted values. When we look at the residuals versus predicted plot, what we're looking for is randomness. Points should be randomly scattered around the zero line with no discernible pattern. We're looking for homoscedasticity so that there is no systematic change in the spread of residuals where it fans out as the predicted values increases or decreases. We look for outliers and patterns such as curvature in the residual plots to indicate that there may be potential violations of the assumptions of the linear regression. And we also look for the overall fit. A higher concentration of the residuals near the zero suggests that it's a better fit, that there is less of a difference between the actual values and the predicted values. Okay, here we are in our Google Colab. We're going to import the packages that we had the last time, but just slight modifications. So we're going to import pandas as PD, import numpy as np, import matplotlib, so that we can visualize we're able to visualize our residual versus the predicted scatter plot. And from Scikit-Learn dot metrics, we're going to import our R2 score and our mean squared error. And I'm going to actually do like I did before. Keep this part. So we're going to import our linear model, which we have linear model, and it's going to import regression. We'll also import model selection with our train test split. We'll also import pre-processing. And this is where it's a little bit different too, because with pre-processing this time, we're going to include not only one-hot encoding, but we're also going to include polynomial features. And we'll finish with, as we did before, we're going to, from the compose package, we're going to import column transformer. To find out more information about the polynomial features, we can go to Scikit-Learn, and here it talks about the polynomial features. That the default is degree 2. You can include an interaction term if you want to. Right now it's false, and so forth. So you can read a little bit more about it. We're going to keep most of the defaults. Okay, now that we have this, let's go ahead and run that. This data set, as I mentioned before, is the medical insurance data set that we worked on within the previous video on multiple linear regression. And we're going to read it in and take a look at the first 5 rows for this data set. If we look at the second row, we have an 18-year-old person that is male. He has a BMI of 33.7, 1 child. He's not a smoker. He lives in the southeast region and has medical charges of $1,725.55. The charges column is our ground truth, our target, or our dependent feature that we're trying to predict. This bit of code allows us to subset our data frame to those columns that are categorical, that include equals object. And from there, what I want is just the column names. I don't want the data frame. I want the column names, and I want to put those column names in a list. And so we end up with the categorical columns of sex, smoker, and region. Now we want to separate the features in the target variable. And we're going to drop the charges column from the X features. It's a column, so axis is equal to 1. If you're dropping rows, you would say axis equal to 0. Our YSD of charges. We had this in a previous video where we did the one-hot encoder, where what happens is our sex column is male and female. That's the subcategories. And so it creates columns for each of the subcategories, and we just drop one of the columns so we don't have redundancy or multilinearity in the data. And so this is what this does as a reminder. The column transformer does operations on individual columns. Here we put a one-hot in front of those columns that we're going to do one-hot encoding on, and that's the categorical features. This one-hot encoder converts the categories to zeros and ones. So it's a numeric, instead of just male female. We have in the male column we have 1 to indicate male, 0 to indicate female, and so forth. And this is going to be done on those categorical columns. The remainder equals pass-through. This is where the numeric features are just going to be added without anything happening to them. They won't be dropped. If you want to drop them, you can just say remainder equals drop. But the remaining columns we want to pass through. We want to keep those in the data frame or in the array. And so this X encoded transformer.fit is just transforms to those categorical columns and keeps the remaining ones as we mentioned. All right, so let's go ahead and run this one. Now we're going to start comparing the multiple and polynomial regression estimates. We have our train test split. We have our X encoded to include those categorical features. Encoding those, that's important for regression, is to convert the categories into numbers. And our test size is 30%. So we have 30% of the data held out, and 70% of the data is going to be used to train the model to create the equation for our prediction. Our random state 413 is the sample. This is sample 413. What happens with this train test split is the data is shuffled. And so we're making sure that we get the same shuffle each time in case we want to compare different models. We can have the same shuffled data or same sample of data. All right, so for the multiple linear regression, we have multiple underscore REGR equals to linear regression. And we're just going to instantiate the model here. Multiple regression dot fit, and we're going to fit it on our X train and our Y train. So here we're creating the model using our training data. Now we're going to predict YPred underscore multiple. This is the name that we're going to give it, and we're going to predict. So we have, instead of the fit, now we're going to do a predict. So we're going to keep this here. And we're going to make that predict. And we're going to predict what the test charges would be. The charges from the test set would be using the X test features. So we have that one. Now let's take a look at the polynomial regression. Just like how we have to do one-hot encoding, we have to transform the features so that they're polynomial form. And we're going to do that by specifying the degree of the polynomial. Degree is equal to 2. Now we could have put the degree of the polynomial inside of the polynomial features, but leaving it outside like this allows you for easy changes or updates. So here we have poly underscore features. This is our essentially our transformer. Polynomial features. The degree is equal to the degree, which in this case is 2. And we're going to convert our X values into a format based off of the polynomial features. So here, poly is trained, it's got poly features. Transform our X train. X poly test is going to be transformed. So we'll take the same thing here. Instead of the fit, we just want to transform it. And it's going to be X test. Okay, so now it's suitable for polynomial regression or linear regression. We're going to say poly REGR is equal to linear regression dot fit on X poly train Y train and our prediction again is going to be equal to predicting on it. So instead of doing this, let me just grab this, as easier to keep from making mistakes here. I'm going to predict on the X test data set. So X underscore poly test. Okay. Here we're going to compare the multiple linear regression with the polynomial regression using our R-squared score. And also we're going to do that using our mean squared error score. So we have our YPred poly. That's right. Okay. All right, so let's go ahead and run it. And what we see here is that for the multiple linear regression, you have 0.74, and for the R-squared score, And here, there was a significant jump up to 0.83, almost 0.84. So almost 84% of the variation that we see in charges can be explained with this polynomial fit when we take a look at the features. Okay. Now, something that you can do if you want to go a step further and just check things that we didn't check last time. The last time we looked at the correlation coefficients and the scatter plots and compared those with the target feature. So we looked at things like age, and we looked at the BMI. So we had age, BMI, and even number of children, and compared it against the charges to sit down and see if there was any linear scatter plot or if there was a linear correlation, and it was very low. So we knew we need to do something different. And so what we can do here, we can also use the residual versus predicted values plot to see if we could have a visual inspection that would also indicate that we might want to do something other than just linear regression. Okay, so here are multiple linear regression. So here, let's take a look at converting our, basically printing out the residuals or getting a visualization for that. So we're going to take our residuals. Here are residuals for the multiple regression. Is residuals is equal to our y test. So these are our charges from the test holdout test data set minus the charges that we got when we did the prediction. So pred underscore multiple. And this plot, this is the size and shape of the plot. The scatter, we're going to do a scatter plot of the multiple, the predicted values against the residual values. Alpha equals 0.5 is just making sure there's a transparency in the plot, so they're kind of light in color. The XH line is that zero line that we've been looking for to see how close those points actually cluster around this line. The color is going to be red, and this is the style of the line that's going to be dashed. Here's our title. The x-axis is going to have the predicted values. The y label will have the residual values. And so this is our grid, and we're going to show it. Let's take a look. Okay, when we look at this, you can see that there seems to be some sort of pattern here, and it's not that consistency throughout. You have a lot of sparsity here. You can see, you look at it, it looks curvilinear. It's a curve here. There's a curve somewhat here. It looks like something that could potentially be an outlier. And I did test it. I actually looked at a ransack method to see if we would get a better prediction, and we didn't. So these are just things to look at. And so this is what the multiple regression residual versus predicted values plot looks like. Okay, let's do the same thing, except this time we'll do this for our polynomial equation. Do the same thing. So we're going to calculate those residuals. Instead of y-pred multiple, we need y-pred poly. So we have y-pred poly for this one. Okay, I think I should get us together. And see, it comes down a bit. Now we have the dots are closer to our y is equal to 0 line, saying that there's less of a difference between the actual values and the predicted values. So here it comes down some. Still see a bit of outlier here. It might take like some subject matter expert or expertise to be able to determine, can we get rid of this or treat it in some different method or way? Is this just a one-off or what, or do you want to keep that in there? So yeah, this is it. This brings us to the end of the video. I hope that you enjoyed this video. If you did, give it a thumbs up, like, subscribe. It's great motivation to keep me making these videos. And yeah, until next time, be well. Peace.